Hello students, and welcome to this chapter 6 where we're going to talk about haloalkanes, their properties and reactions. Remembering that a haloalkane is a carbon chlorine or carbon fluorine or carbon bromine or carbon iodine bond, and so we often just represent that with an X. So again, remember the halogens are fluorine, chlorine, bromine, and iodine. This type of bond gets like a whole chapter because what we find out is just that normal alkanes, so ethane, propane, butane, hexane, all of those are fairly boring. They don't have a lot of chemistry. You can burn them. They take place in radical reactions, but otherwise they don't undergo many more reactions. The carbon-hydrogen and carbon-carbon bonds of alkanes are fairly nonpolar covalent, and so then that doesn't lend itself to bond breakage. And it's because they're all nonpolar covalent. When you add the presence of a halogen, then you polarize that bond. So this bond right here becomes polarized. There is a difference in electronegativity, so remembering that this guy will be partially positive and partially negatively charged, and that difference in electronegativity then allows those bonds to break a little bit easier. Remember, carbon-carbon and carbon-hydrogen bonds, there is not any of this bond polarity. That is, they would not actually have these partial positive and partial negatives. So as we talk about the halogens, one of the things to remember is that the bond strength of this carbon X, so this carbon-halogen bond, it decreases as the size of X increases. So the bond strength goes down. All right, meaning that like a carbon fluorine would be stronger than a carbon iodine, because this one's the larger. Why is that? Well, let's go back and look at some of the bonding that take place. So when we have a bond that forms between a carbon and a halogen, here's the carbon, here's the halogen, what happens is that we get a p orbital on the halogen, the X, fluorine, chlorine, bromine, iodine, and it overlaps with an sp3 hybridized carbon here. So we get this nice overlap that forms. And for fluorine and chlorine, these are fairly strong bonds and fairly nice overlaps. For bromine and iodine, as they get larger, right, so as the size of X increases, this bond, the bond actually strength goes down correspondingly as the size increases, and that's ultimately because there's not as much bond overlap. All right, so that is the size of the p orbital increases from fluorine to chlorine to bromine, and there's a less percentage of overlap, and so hence we get a weaker bond. So for instance, we might say that this one that we have here, this would be fluorine, and that would be the size of its p orbital. Let's pick a different color. We'll just call it green. So imagine if you had something like bromine, and perhaps the size of its p orbital might come out like here. We'd have an X, and it really is this big, and it's probably even bigger, and this might be something like bromine. So it's much larger, and so what that would mean is that the percentage of overlap of the bromine p orbital with the carbon would be fairly light. All right, so it would be fairly small, and so as a result, then there would not be a really strong bond. All right, so because of the weak overlap that occurs here, the bond will not really be that strong. It would be easier to break. I say not that strong, but compared to, say, a fluorine atom or something along those lines. Now, it's table 6.1, we can see that here. So again, it's the carbon X bond length and the bond strength. So notice, let's just take a look at this. Say the halomethane is a fluorine connected to one carbon. Notice its bond length is about 1.385 angstroms. Remember, angstroms is 10 to the minus 10. And then notice that its bond strength, we'll just look at it here in kilocalories. The first one's at 110. If we go to chlorine, notice the bond gets longer. The bond strength goes down. That means it becomes easier to break this bond. Bromine, a little bit longer and weaker. Becomes even less energy to break this one. And then the iodines, significantly longer. And again, notice that the bond strength is about half that of fluorine. Why is that again? Fluorine's smaller, has better overlap, better percentage overlap, forms stronger bonds. Something like bromine, iodine, much larger, and so ultimately the bond is weaker. Bonds being weaker is sort of okay. That means it's easier to break, like a carbon-iodine bond. And that actually can be good for some reactions if you're trying to get something to occur. We're going to see some of that in this chapter and also in the lab as we move forward. All right, so let's a little bit about some of the physical properties. Again, I've already mentioned that the carbon-halogen bond is polarized. And that's because they are more electronegative. Remember that the halogens are to the furthest right, not of Nobel gases, but furthest right of anything else that has an unfilled octet shell. And so it's more electronegative, and so they polarize. The halogen atoms, again, possess the partial negative charge, as I showed earlier. We see that here, and the carbon has a partial positive, so making that difference. And we often say that a dipole moment we put on here, and the way we showed is going from this direction. So you can think about there's a little positive charge here, showing the positive end going over to the x. One thing to note about this is that if you've taken physics, oftentimes they will draw their dipole arrow in the opposite direction. All right, so just by convention, they're showing where the electronegativity is higher and then to the lower. But we're going to continue to show our normal arrow that we see here. All right, so very polarized. One of the ways that we can visualize the polarization is through these maps of electrostatic potentials, MEPs as they're sometimes called, but map of electrostatic potential. Notice that this represents the carbon and hydrogen atoms that are here, and then over here is the halogen. Notice the halogen is more electronegative, so it's pulling the electron density to it, so it's a little bit red, and then the cooler spot is over here where the carbon is, and that's partially positive. All right, and so, and again, notice that these are from the textbook, and they've color coordinated them as such. The bluer is the cooler, less electronegative, and the red is the hotter and more electronegative that we see here. So these maps of electrostatic potential can be helpful. And one of the ways they're helpful is they show this electronegativity difference and within this and how the electrons are arranged. And whenever you see sort of this large difference, you know it's likely that there's going to be a chemical reaction occur there. And why is that? Well, this electrophilic carbon, which is partially positive, is subject to attack by other anions. So because it has a partial positive, that really attracts anions, things that are negative that can come in here and attack it. And so that's increasing the reactivity, and that's really and that's because these carbocations, and this one's not quite a carbocation, but it's becoming partially positive, and other things outside could actually attack this electronegative atom and actually pull it off, this halogen that's here. All right, so it's all because of this carbon bond is polarized. Once again, we do not see this polarization, the same type, in a carbon-carbon bond or a carbon-hydrogen. They're nearly equal. Because halogens are present, they can actually have a higher boiling point. Maybe you saw this if you had a chlorine or a bromine group in your unknown in lab, and because they are larger, they end up giving higher boiling points. Well, they're larger, but sometimes they, like iodine, they can be physically larger. But because of this difference in electronegativity that we see here, it can actually give them a higher boiling point. All right, so large iodine can, just because of London forces, but what we're talking about here primarily is because of this difference in positive and negative, and that can result in a dipole-dipole attraction. And remember, this is a non-covalent force. Non-covalent forces include hydrogen bonds, which are the strongest, then these dipole-dipole interactions, and then London forces. All right, so the bigger the dipole here results in a larger dipole-dipole interaction, and hence these molecules stick together better, and then that relates to a higher boiling point. All right, and so that's one of the keys, attributes of these carbon-halogen bonds, that we can see that. And not only does it affect boiling points, but it would affect melting points and other properties as well. But the one that we've seen most prominently are indeed the boiling points. As I mentioned earlier, that there is the larger London dispersion forces I was talking about with iodine, and so that's also important, just in terms of the size and the number of electrons. But then also something like bromine and iodine, they're actually more polarizable because they just have more space, and that also, those interact through London forces as well. So the key thing is non-covalent forces are a key attribute of these carbon-halogen bonds. So some of the chemistry is fairly fascinating for these haloalkanes. Some of it is not so good. It has its bad things. So it's always good in science to think about, all right, what is the benefits, in terms of making better medicines, better molecules that make up things that are like better materials. However, they can have some harmful consequences, and we need to realize that and accept that and actually move to make them better. One of those is chlorofluorocarbons, and these are compounds that are used in refrigerants, and they're very good for that. However, they're also very good at breaking down the ozone layer. All right, so this would be a chlorofluorocarbon. So there's the chlorine and the fluorine, and those actually react with ozone if they're released from refrigerants. They break down the ozone layer, and we know that the ozone layer is helpful in keeping out UV light. So most governments have started to ban these, and most chemical companies have found good alternatives to this. All right, so one example of, again, this having a good effect on cooling, however, a bad effect on the environment, and so people are taking steps to actually change that and make something that's less harmful. Drinking water is one of the places we can find these. Trihalomethanes, or TTHMs, or actually THMs, but total trihalomethanes is TTHMs. And these are compounds where there's one carbon and 3 halogens. Here I'm showing the 3 bromo group, so it's bromoform, but you could have 3 chlorines there, or maybe 2 chlorines and a bromine, or 2 bromines and a chlorine. The chlorines and bromines are most common. These are formed from naturally occurring bromines or chlorines that are possibly in the water. However, they're mostly formed when we add chlorine to water to disinfect it, and it does kill bacteria and those types of things, but if we add too much of it, we can generate trihalomethanes, which consumed over a 40-year period can be harmful. All right, and so in the water treatment industry, they've actually changed and still use chlorination. However, they've started to change to use other types to make this actually not as harmful to humans, but it's still the benefit of adding chlorine to kill the bacteria outweighs any long-term effects at this point, especially the way it's regulated in the United States. And then finally, some of the bad things that can occur, we often have coatings on Gore-Tex jackets, ones like this Patagonia jacket, but many other brands as well. Gore-Tex is great if you're into mountain climbing or hiking or hunting, fishing, you might have a Gore-Tex jacket. And what makes it so nice is that there's a lot of fluorine on these materials, and so it does not let water through, and so water runs off of it. And they're also very porous, so they let sweat out from their body, and so they're actually quite comfortable in rainy and cold weather. However, these fluorines have been found to not be so good for the environment. So again, companies like Patagonia and many of the others have started to develop a better Gore-Tex material. All right, and so that is coming. So again, these are just some of the negative impacts of haloalkanes, things that we as scientists and engineers need to realize and to appreciate and to develop better things that are better. Well, we talked just a little bit about the chemistry of haloalkanes. One of the important reactions that haloalkanes can undergo is a nucleophilic substitution. And to understand the nucleophilic substitution, we need to back up, and we need to think all the way back to Chapter 2 and a little bit later, and even some of our reaction journal entries to think about nucleophilic substitutions. So, what are nucleophiles? Well, first of all, we need to review acids and bases. A Lewis acid, you might recall, is a species that has an atom that's at least 2 electrons short of a closed outer shell. All right, so the closed outer shell means it's satisfied, so 2 or 8 electrons. So this H plus is a good Lewis acid. This boron, remember, just has 2, 4, 6 electrons, so it needs 2 more, so it's a good Lewis acid. And this, what we call a carbocation, a carbon that has a positive charge. It's also a good Lewis acid because it, again, is missing a pair of electrons. Again, going back to our haiku, remember we talked about the Bronsted definition. So this chemistry haiku says, Bronsted says give H, Lewis says take electrons, acids will do both. All right, and so that's really what an acid is. And thinking about it's either giving electrons, taking electrons or giving a hydrogen. A Lewis base is a species with 1 lone pair of electrons, at least 1 lone pair, it could be more. So that would be something like what we think of as a traditional base, OH minus, but also the electrons that are on this alcohol group of this methanol, electrons on this nitrogen would work, and then also the halogen. They have lots of unpaired electrons, and so those actually could make a Lewis base as well. All right, and so really understanding nucleophiles and electrophiles gives us a good sense as we review bases and Lewis acids and bases to remember what they are. All right, so let's use this idea of acids and bases to help us understand better what nucleophiles are and really what electrophiles are. All right, so many organic reactions, including the SN2 reactions that we're going to talk about in this chapter and the nucleophilic reactions, they really resemble an acid-base reaction. All right, so we talked about on the last slide, all right, Lewis acids and bases and what are nucleophiles. If we go back here, I just wanted to point out that we're talking about nucleophiles, and so the Lewis base really is a good nucleophile. And so let's go back forward. So again, we're thinking about what those are. So we're going to see this Lewis base, which is a good nucleophile on the next page. We're also going to need Lewis acids, which are electrophiles. All right, so here's that OH minus. All right, so it's a good nucleophile, and it's negatively charged, and it's really looking for something that loves electrons. And that would be this carbon here attached to a chlorine. Now you might say, why would that carbon be looking for electrons? It already has 8. Right? It has 4 bonds, 1 to the chlorine, and then it has 3 bonds to that hydrogen. Recall, however, that that carbon is going to be partially positively charged. We get a better color here. It's going to be partially positively charged because it's attached to that chlorine, and the chlorine is going to be partially negative. All right, so that carbon is actually going to be a good electrophile because it's somewhat deficient of electrons. It does have 4 bonds, yes, which would be electrons, but remember this chlorine's pulling them away, so it's exposing that carbon, making it a little bit partially positively charged here. And so then the OH can come in and attack it. So the OH, which is a good Lewis base, comes in and attacks the electrophile, which is a Lewis acid. Remember, a Lewis acid is really 2 electrons short of a full shell. This one's not quite there, but it is deficient in those electrons. All right, so it's breaking, or it's attacking, and this is willing to break a bond with this chlorine. So really, what we can say is that all Lewis acids are electrophiles. All right, so all Lewis acids are electrophiles. They're really deficient in electrons. And all Lewis bases are nucleophiles. All right, so these guys have lots of electrons, and they're really looking for something that's more positively charged to share them with. All right, so this is electrophiles and nucleophiles. So when we start to think about a nucleophilic substitution, we really do think in this terms of Lewis acids and Lewis base, with the nucleophile, of course, being the Lewis base. So this is characteristic of this particular generic reaction. It's very characteristic of a nucleophilic reaction, where you have this nucleophile, something with a pair of electrons, and that could be an OH minus or something else, and it reacts with this electrophile, and this would be a carbon to break apart, and we end up with the R group bonded to the nucleophile, and this other group, which is likely going to be a halogen in our case, is going to be a good leaving group. All right, so really 3 of the major things: we have a nucleophile, an electrophile, and a leaving group that goes away. All right, and so again, why does this happen? Well, there's an attraction between these negatively charged electrons and the partial positive charge of the electrophile, and then it can only form 4 bonds, and then so that's why the leaving group goes away. And so this is just sort of a characteristic. Let's talk about these a little bit more in depth, some of the key players. Another term that we can use for one of these is the substrate, and that's the organic material. This guy would be the organic, the carbon group, and that's really going to have the electrophile, the nucleophile, all right, which is this Lewis base, and it's going to be attacking, you can think of it. And it's really maybe more of attacking, it's an attraction that's happening there, almost like a positive-negative, magnet type of attraction. And then finally, as I said, we have this leaving group. And the halogens are a really common leaving group, and we'll talk a little bit about why that is in just a second. All right, but this is sort of a classic leaving group. All right, so this is what the characteristic nucleophilic substitution looks like. And I'm going to draw out sort of the general, a more specific nucleophilic substitution from the general one that we just saw. All right, so imagine if we had a carbon here that was bonded to a bromine. And of course this would give us a partial negative, and this will be a partial positive charge. But then let's add on some other components. I'm going to put a hydrogen here. Down here we might actually draw out of another R group, and so this might be something like CH2 and then a CH3, so a 2-carbon group that's going behind here, and then we might also draw out a methyl group that's here. Alright, and so again, recalling that this is what we just saw on the last page would be a substrate. This is going to be our leaving group that can occur. Well, what else happens? Well, we also had something that's important, is we had an iodine, negative charge there, and the iodine can actually serve as the nucleophile that is the Lewis base. All right, and so it can come in and attack this carbon here, and then overall it's going to remove the bromine. The bromine is going to become the leaving group. And by the way, just so we recognize this, this is 2-bromobutane. We've seen that compound a couple of times in class. So 2-bromobutane, here's a little bit different. And it's going to react, and it's going to be an equilibrium reaction where it ends up, what we would end up getting would be the iodine, which is coming in from the back side. It forces the bromine away, so it forms with itself, with the carbon itself, a covalent bond. And back here we would have our methyl group that would sort of pop over. And then here we're going to have our CH2 that would form, plus we're going to get our bromine, which goes away. Remember, it takes 2 electrons, the bromine does, from here, and so it ends up with a total of 8 electrons, and then we can add in our electrons for the iodine, and so we end up with this product. Alright, so again, the nucleophile comes in and attacks the substrate, as we call this whole thing. This also is the electrophile, the electrophilic carbon. The bromine is the leaving group, so it comes in, attacks here. We have to draw an arrow there. We end up with this product, which is really just 2-iodobutane, and then we end up with the bromine. Alright, so notice this one both involves halogens, and we'll find out that that is indeed the case. You might ask, why in the world do we have arrows like this? And this is what we often see as equilibrium arrows like that, equal size. But these arrows right here are different size. And oftentimes we'll use different sized arrows or differently sized arrows to show which direction it's moving. So the larger arrow means that there's more reaction going in that direction, and the smaller arrow means there's less of a reaction. All right, so just a little visual cue there to show you where the reaction is going. All right, so this is just a little additional reaction to show you more specific nucleophilic. We're going to see a lot more of this in lab and also in lecture in the days to come. Finally, I want to point out that nucleophiles, they can exhibit considerable diversity in terms of the types of products that we're ultimately going to get. All right, and so just showing you a couple of these, again from this table 6.3, is that we have a nucleophile that's an OH group, right? So this is a base, it comes in, attacks here, and we end up with an alcohol. We also might have this group, which is basically a methanol with an H removed, really strong nucleophile, and it can attack, and we end up with an ether. And then finally, we have a halogen that's a nucleophile. We also have a chloroalkane, a bromoalkane, but a haloalkane, and then we end up with another alkane, a new haloalkane is formed. All right, so we have just a variety of these, and of course even this fourth one is even more different than the other two. All right, so just know that we get, there are a variety of nucleophiles that we can use, and table 6.3, this is just 4 of them. Finally, the leaving groups are important. Halo groups, as we saw, can be reversible, so you might think back to the reaction that I just drew out, and then we had 2 different sized arrows with the iodine and the bromo group, so they are both reversible, so they can serve, interestingly enough, as nucleophiles and also as leaving groups, and that's why they're reversible. And that actually is not a bad property, allows them to be reversed. On the other hand, if you have nucleophiles such as an OH minus and CH3O minus, and those attacked as nucleophiles, they are not good leaving groups at all. all right, because they're strong bases and they actually want to remain attached to the carbon. All right, and so they are not good. And so that actually can be good because that way you can get a product and then you're sure that it's not going to break down and to move on to something else. All right, so this is the first little bit of understanding of nucleophiles. One of the key things that we want to understand in this section is that we do have haloalkanes, and haloalkanes, this carbon X bond is polarized, partial positive, partial negative. As a result of that difference in electronegativity, that leads to some physical properties like higher boiling points, but also to greater reactions, particularly nucleophilic reactions that start because this carbon is partially positively charged and something else can come in and attack it. Something else can come in and attack this negative like a more positive thing. But the ones that we're looking at is we have negative charges coming in, attacking that partially positive carbon. And that has sort of set up some of our first chemistry that we're going to see with haloalkanes, which are these substitution reactions, these nucleophilic substitution reactions.